right, hello everyone. So today we're working with a probability problem. It's a binomial probability. And suppose there is a 97% chance of a device produced by a company works as intended. So 50 devices are randomly selected. What is the probability that A, all work, 7 are defective, at least 1 is defective? Okay. So let's look at what binomial probability is. So suppose there are independent trials. What that means is that you're going to do some type of experiment in a sense, n times, and the result of one experiment is independent of the previous one. That is what we mean by the word independent. And here are n, for example, would stand for like 50 for, let's say, look at part A. Because it's 50 devices, like 50 trials, 50 experiments, let's say. Like if you flip a coin 20 times, let's say, n would be 20 there because you did 20 flips. Okay, and a couple other things that we're going to look at. There's a p chance of success and a q chance of failure. And those are the only outcomes you can have. This is what we call a Bernoulli trial as well, where there's only two outcomes, success or failure. And success and failure always add up to 1. So p plus q equals 1. And p and q are decimals or fractions, whatnot. And the probability of having r successes is given by that formula that you see here, which I'll read off. N choose r times p to the r times q to the n minus r, where n choose r is n factorial divided by r factorial times n minus r factorial. That's what n choose r means, okay? And let's go ahead and kind of apply this to the problem that we're working with. So we were interested in looking at what is the probability that they all work, okay? So the probability that they all work would be given as such, 50 for n, because I have 50 trials here. My success percentage 0.97, or the decimal, excuse me, is 0.97 or 97%. Q is 0.03, and that's the failure. And then my R is 50 because I'm interested in choosing 50 devices that are working. So 50, choose 50. P is 0.97 to the 50th power, and then 0.03 to the 50 minus 50. That would be 0.97 to the 50th power. Because this is 1 and this is 1, so it's like 1 times 0.97 to the 50th times 50. And you come around with an answer that's approximately equal to 2.218 or 21.8%, okay? So basically we're saying that if you were to select all of these devices, the probability that all of them would be with no failure would be around 21.8%. Okay, so how about now for part B, the question is how many devices are defective? So here your n is 50, but pay attention to this though. P is going to be 0.03 this time because I'm interested, success for me means not that the devices work, but that the devices don't work, okay? Because I'm looking at the number of things that are defective, and that's why I'd have a 0.03 for my P. And then Q would be my failure, and the failure in this case would be that you have the devices working, that's 0.97, and your R would be 7 here. So the way this would work, if you were to plug this into your formula, this would be 50 choose 7, P 0.03 to the 7th power times 0.97 to the 50 minus 7, which is 43. So I'll rewrite that as 43. Now, this is where you would really have to use a calculator. Well, even for the previous one, but specifically here because of that 50 choose 7, that's a huge number to work with, in my opinion. So I'd rather just use a calculator. And we went ahead and did that. This is what I got. Let's look at, sorry, not Desmos. There we go. 50 choose 7 times 0.03 to the 7th times 0.97 to the 43 power gives you 0.000589, okay, and 56. So I'm going to rewrite this with 0.000589. So as a percentage, this would be 0.0589%. So there's a really small chance. Okay. And then the last question here was that at least one of my devices is defective. So when we say at least one is defective, that could mean that one device is defective, which I'll just write as P of 1 here just for shorthand. And also it could mean that two devices are defective, P of 2, can be P of 3. It can go all the way up to 50, okay? And really for me to calculate this answer, I'd have to, well, technically speaking, I'd have to calculate each of these and add them all up together, okay? And that would be my answer. However, that's really daunting. It's going to take a long, long time. I would use my binomial probability and plug each of those in. So probability of 1, probability of 2, probability of 3, defective into my binomial probability formula up to like 50. So each individually, that's what I'd have to do. So what's the alternative, if any? Well, here it is. If you have an event, call it A, you have its complement, okay? So the complement, basically, it's like the opposite of the event in a way, of event. So for example, in our case, the event that I'm looking at is that at least one is defective, okay? So what's the complement of that? Well, like the opposite. What's the opposite of at least one defective? Is that there are no defective, okay? Or that they all work. And there's a rule that says this, that if you take the probability of an event happening plus the probability of its complement, it's equal to 1. So the probability of an event, you can take 1 minus the probability of the complement. And how does that work to our advantage here? Well, the probability of at least one defective is equal to 1 minus the probability of no defective or all work. Well, we already figured that out from part A. It's 1 minus 0.218 here. And if you subtract those two from each other, you would get 2 8, and then you would have a 0.782 here, okay? So a 0.728 probability or 72.8% chance that at least one of them is defective, okay? So that's what we'd be looking at here. All right, so there we go. In terms of, again, this is a really good tool when you're trying to find the probability of n successes, r successes, excuse me, r failures here out of n trials. So you do an experiment n times, you want to know how many times you're expected to get success or failure. That's what a binomial probability is useful for, okay? Just don't forget that your events have to be independent of each other. You can't have that dependency. And yeah, that's the thing to note of really there. Okay, well, thank you so much for your time. Appreciate it. Hope this helps.